Thank you. Hello everyone. I'm Pankaj. I'm a PhD student at IIT Kanpur. So this work is so today we'll talk about synthesizing abstract transformer. This work is with Sujit and my supervisor Subhajit Roy from IIT Kanpur, and our collaborators Loris and Thomas Reps from University of Wisconsin-Madison. So so abstract interpretation is like some approximation of the program semantics, and we reason about the program using an abstract domain. In this example, we'll take the interval domain where the alpha function, which is the abstraction function, takes a set of concrete values and maps to an abstract value. Okay. Now, the gamma, the concretization function, it takes an abstract value and maps to a set of concrete value in the concrete domain. But there exists a function called beta, which takes a single concrete value and maps to an abstract value. In abstract interpretation, the main the tricky part is to come with the abstract transformers. Given the concrete domain and an operation f, which takes a concrete value and maps to another concrete value, we one need to come up with an abstract transformer f sharp, which takes the corresponding pre-abstract value and maps to the corresponding post-abstract. Now, in practice, this is even for the trivial operation to come up with an abstract transformer is hard, and if you write manually, it's very error prone, and we have proof for that. Okay, so let's state our problem. So can we automatically synthesize this abstract transformer for any operations? Formally, given the concrete semantics of the concrete transformer F in the concrete domain, and a description of the abstract domain and the relation with the concrete domain, and a domain-specific language L, so it's synthesis, so you need to have that L. So can we synthesize the best abstract transformer F sharp hat of function F for an abstract domain A in the given language L? Now, what is this best abstract transformer F sharp hat? So you see, so it takes the join of post value by applying beta or for the each concrete value from the gamma of A. Okay. Now let's take a simple example. Now we all know the absolute functions and we all know the interval domain. And given this a simple trivial language, what will be, we'll try to get what will be a abstract transformer for absolute in the interval domain. And this error and error are the limit of the input in range. Now we can come up with the transformer which is shown in the here. Now I can see the left part, so it contains of left and right. The left part is contains two maps. So you see for even the simple operation absolute, it's little tricky. And we can come up with another transformer, which is little trickier than the earlier one actually. So if you see the both of them are sound and precise, but they are not comparable. Okay. Now what are the challenges in this problem? So the problem is that this F sharp hat, the best abstract transformer, may not be computable. Now, this even not be expressible in terms of the language we given to the system. Now the precision of these transformers from a partial order, and there might be many solutions. The F sharp hat might not be unique. So you can come up with a trivial example where you can say there exists more than one best and sound abstract transformer. Okay. Now let's come to some notation before we jump into technicalities. So why do you say an L transformer, F sharp L, is a transformer which from the language L? And we said best L transformer. We say an L transformer is a best L transformer if the transformer is sound, obviously, and there doesn't exist any other transformer in L which is more precise than this given transformer. Okay. Now, if you get confused, so this sharp means if there is a sharp on top of it, it means abstract domain. If there is a hat on top of it, it's a best. And if there is L is sticking with it, it means from the language L. For simplicity for the coming up slides. Okay. Now, let's revisit the problem statement we have defined earlier. So we have said that given the inputs, can you synthesize the best abstract transformer abstract head of for abstract domain A in language L? Now, since you know there is no might be so the challenges we have seen, then we refine our problem so that let's synthesize a best L transformer f sharp L of function concrete function f for the given abstract domain A in the given language L. Okay, so we build the tool AMURTH which solve this particular problem. In Hindi, the native language of India, the AMURTH means abstract. So what we can say is giving a solution for this problem, we can say that we can build abstract interpretation engine for free. Now, who cares? Why do we need to synthesize these things? The abstract interpretation, their transformer in abstract interpretation engine, it's tricky to come up with. You have seen that for the simple operation and simple domain interval, the operations are tricky. And the manually written abstract transformers are error prone. Now you may ask it, are you sure? Yes, we are, because we found multiple bugs in manually written transformers in the existing abstract interpretation engines. Okay, this AMURTH is pretty reasonable. It takes pretty reasonable time to come up with this non-trivial transformers. Okay, let's see how it works. Okay, so AMURTH uses a SEGIS strategy. So SEGIS stands for the counterexample guided inductive synthesis. So we try to, since we are trying to synthesize a transformer, we try to meet the dual objective, soundness and the precision. So since we have a dual objective with this, the algorithm is driven by the two kinds of examples. The first one comes the positive example. What do you mean by positive example? We say an A C prime. Now this is a tuple of an abstract value A, and the C prime is a post after applying the function f, post value, such that A comes from A is an abstract value and C prime is is included by the best abstract transformer, not the best L, the best abstract transformer, F sharp head. That is a positive example. Now the violation of this sound, now the positive examples come from the soundness verification in our tool. This, the violation of soundness verification gives us the positive example. Now let us take this example. Now you see, so it's a tuple. So there is a range 5 to 9 and it says C prime 6. Now I can make you convinced that there doesn't exist any value. Sorry, there exists a value from 5 to 9 on which if we apply absolute, we can get 6, which is 6, right? Okay, so the examples I'll be talking about in this talk will be in interval domain and mostly in absolute, unless specified. Now the second kind of examples we talk about is a negative example. So negative examples is also a tuple of A and C prime. Now with the negative examples, we try to find an example as well as then a function and another best abstract transformer such that the C prime is not within the F sharp L of A. Okay, so we're trying to make the precision. Okay, that negative example is generated by the precision verification engine. Now let's take the same example with the 5 and 9 abstract value. Now I can say that there doesn't exist any value between 5 and 9. If we apply apps, we'll get 2. Okay, this is an example of negative example. This counter example generated by this soundness and precision verifiers drive this 2 SEGIS law. So this AMURTH is driven by the 2 SEGIS law, not a single one. Okay, let's see a pictorial representation how we try to synthesize this transformer. Now in this figure, the purple one or blue is the transformer we are synthesizing in this moment, and then the dashed line is the best transformer we have. We don't know what is the best transformer, but there exists the best transformer. Now in the beginning, we assume that there we have a transformer which here it takes a value A, but it returns a constant range 0 to 2. Okay. Now we find a positive counter example to this transformer. Okay, now we see it, so it returns from 0 to 2, but if I give input 0 to 5 and 3, we say that 3 should be between 0 to 5. And the C means there exists a value between 0 to 5. If I apply absolute on that, I'll get 3. So I should include 3. So what we do is synthesize again by including the positive example. So the positive example is to include. We include them. Now we synthesize another transformer. And now it's from 0 to the summation of the both limits. Okay. Then we find a negative counter example. Now you see here in the example, the range is 3 to 7 and the C prime is 8. So we know there is no way we can get 8 from any value from 3 to 7 for the given thing. But you see, but for the given transformer 0 to the sum of this, it will be 10, 0 to 10. So 8 comes in that, but actually it shouldn't be. So it's a negative example. So what we do? We shrink it. We try to synthesize transformer which to include the positive example and exclude the negative example. And these loops keep on going around until the both soundness X and persistence X keeps on. Now, schematically, this is our algorithm. So we have two loops. In the left, we talk about the soundness. It checks soundness and it gives the positive example. In the other side, there's a check precision loop, which try to check whether the synthesized transformer is precise or not. And in the middle, we try to synthesize the transformer. But it's not the complete story. Some additional algorithmic components are needed to work it around, and I encourage you to read our paper on that. Now, what are the claims we made in our paper? So we say, first theorem, we say that if our algorithm terminates, it returns the best L transformer for the concrete function f. Now, in the second claim, we say that if the DSL L is finite, the algorithm always terminates. So what you can say, if the DSL L is finite, we get the best L transformer for concrete function f. Now, let's talk about the evaluation, what we did and how we have. Now, we have done two case studies while trying to synthesize that. First one is on string domain, and the second one is fixed bitwidth interval. In string domain, we have looked into 5 domains: constant string set, character inclusion, prefix, suffix, and string s. And in case of bitwidth interval, we look into 3 domains like unsigned integer, signed integer, and ref interval. And the operation for string domains are like caret, concat, contains, to lower, to upper, trim. And there are 9 operations for the fixed bitwidth interval. Okay, fine. Now, how do we evaluate whether the transformers we have synthesized is it's worth it or not? So, what if we take an existing abstract interpretation engine? So, since it's an abstract interpretation engine, it will have some manually written transformer to it. So, we take it and we remove them. And what we did is we plug it our synthesized transformer by AMURTH. Surprisingly, in case of performance in terms of analysis time, imprecision index, fixed point iteration, and program state, we did same as the manually written transformer. Okay, so far so good. But we did find 4 soundness bugs in the manually written transformer. Let's talk about, among 4, let's discuss one bug we found in the contents concrete operation in character inclusion domain. Before jumping into the problem, let me discuss about the character inclusion domain. So it's a string domain. It is defined by 2 set of characters. One is called must set and another is called may set. So the must set is a set of characters which must be present in the abstract value defined in the must set, and the union of all characters present in the abstract value is given in the may set. Now take this example, fan and ran. Since A is both in fan and ran, so the must set contains A and the may set contains F and R. Well, A should be also there. No, I missed it up. Sorry. Okay. Now, since we have got the hang of the character inclusion domain, let's talk about the bug. So there are 2 transformers I have shown, and one with the red boxes and one with the blue boxes. The red boxes one is the manually written transformer, and the right one is the synthesized transformer. Now in these 2, line 4 and 5 in the left box, it says the precision bug, and the line 8 shows the soundness bug. Now in contents, the concrete operator contains, it takes 2 strings, string 1 and string 2, and it returns true if string 2 is a contiguous substring of string 1. Otherwise it returns false. Okay. Now let's see where it goes wrong. Now take these 2 strings, S1 and S2, these are concrete string, where S1 is a 2 times repetition of A and S2 is the 5 times repetition of A. Now we are sure, we can say that S2 is not a part of S1. S2 doesn't contain in S1 because S2 is. But if we get the abstract value, now A1 is the abstract value for S1 and A2 is the abstract value for S2. Now I say it's both are same because the characters are A and main mass contains A. Okay, so now we have A1 and A2, both are same. Now look at the code in the left hand side. So it takes the contents original text 2 value. Now let's see in line number 8, there is some condition. So is there that this U stands for the may and L stands for the must. So this A2.U means this guy, the may of the second guy, is less than or equal to 1, which is true, and his subset A2U and whatever it is, they are all same, so it satisfies. Nothing to worry about. So it returns bool true. So the output of the contents in abstract domain, it takes Boolean lattice, top, true, false, and bottom. Now we see that we know S1 doesn't contain S2. Still, the abstract transformer, the manually written one, it returns bool true, which is soundness bug. And we fixed it in our the right hand side, the blue part, the line A. It says that if A2 is empty, then only return bool true. Actually, this is the case. You cannot come up with, it's in the character inclusion domain, only you can say bool true only if it's the second is A2 is empty. Because empty is empty combination everywhere. Now let's talk about the line number 4 and 5, which I have said is a precision bug. Now what it says, it's a simple check. We do if both of them are top, then it's a bool top. Now see, let's consider an example where A1 is top and A2 is empty. In that case, it's true, right? Because empty is in top, but it returns top. So that's the precision bug, right? And in our case, it's not there. So there are other bugs which is, or I encourage you to read in the paper. Now let's, to conclude our talk, these current techniques at handling such operations, either very highly imprecise, unsound, or manually an error. Our tool automatically AMURTH automatically synthesize non-trivial abstract transformer, and the bugs we have shown, the bugs we have found, it's worth mentioning that AMURTH was capable of doing such things. Last, I want to thank Google for granting the travel grant to attend SPLASH. And with that, I want to conclude my talk. Our artifact is available. It is another Docker file, so you can look into it. Thank you. I'm ready for questions.
Thank you. Questions, please. As well.
Thank you. Thanks for the talk. If I recall, one of the things that we used to worry about in our abstract interpretation was composition of transformers.
Okay.
Because the best abstract transformer didn't distribute over composition. So the best transformer for F and the best transformer for G, the abstract composition didn't get you the best transformer for F and G. Right? And so I'm wondering about the scalability, and if you had any assumes or any sense, if I wanted to do, a basic block of transformers and get the best abstract transformer from the basic block, would you scale for that?
Yeah, currently the scalability might be there. So we have not done experiment on that, frankly, but I do think the scalability might be. So we might have to come up with this algorithm might, but we have to come to something little tricky, so to solve the problem.
Okay.
Yeah.
Sure, please.
So my other question is, assuming you didn't want to use the synthesis for some reason, maybe it doesn't scale, do you wind up also having a good way of just testing by manually written transformers?
Yeah, good point. So I want to clear that. So while I was talking about the bugs, it's not that we try to test whether it's there. We find out that we try to synthesize something and we check, oh, it's not matching. Why? So we come up with, oh, it's a bug, something like that. But I think we can use that for testing because we don't have to synthesize now. We have to find whether it's correct or not. Given the loop, we have the precision and soundness, whether the given loop, given a transformer, because now you're talking about testing, we have a transformer for that. We'd like to say whether it's sound or precise. If we get answered somewhere, we might be able to say, okay, we have a valid proof that it's not precise, or we have a valid proof that it's not sound. Does that answer your question?
Yeah.
Bring and then. Oh, okay. There's another one. Okay, go ahead.
Yeah, thank you for the talk. So, can you comment what abstract engine you use to find those bugs?
Yeah, so it didn't come in the so we use some tool called Safe. It's a string JavaScript abstract interpretation engine where you try to find a violation, assertion violation, and all. So you use that. We take the Safe and we do little engineering where we remove their manual and we put our plug.
Hi. So, how long does it take to actually synthesize these transformers?
Oh, it varies a lot. I mean, I cannot give a correct answer, but as I have seen in the slides, maximum is 1900 something seconds. Something is that. Like it's like less than 2000 seconds. Both.
Okay. So I was wondering if you have, or if you have thought about a clever way of generating these these examples. Maybe there is a way to generate examples that sort of speed up this synthesis process.
Yeah, I think there might be a possible way currently.
So we have a few optimizations, like for example, so one way to do that is to start with a set of examples rather than generating everything in a algorithm manner. And so we do fuzz in the beginning and create some examples to start with. We call them bootstrap examples, so that speeds up things. We have a few more optimizations where certain times we try to lift our examples to a slightly called abstract example, that sort of thing. But again, there are more we can do, of course.
Yeah, hi. I was just curious. I don't know too much about how abstract transformers are actually implemented, but I can imagine for complex domains since the best transformer is actually both expensive computationally, and so the implementation may intentionally be less precise. I was just wondering if you had thought about tuning the precision and performance. Is that something that you guys have thought about or considering for future work?
So you're looking.
Like, we may not want the best transformer because it's just prohibitively expensive.
Yeah.
So you may want something that's more in between. I'm just wondering if you had thought about how to express that in your specification, maybe, or.
So yeah, so the how this algorithm works is that we try to find a sound and precise. I think what you are trying to do is like something in the middle. So maybe you can put some constraint there. Okay, stop there somewhere. I might with the same algorithm might work for your settings. It does that answer your question?
So one more knob that you have is the language.
Yeah.
So for example, the language can sort of only contain programs which are not very expensive.
Yeah, maybe we can talk about.
Yeah.
Yeah.
Another question there?
So I might have missed that in the slides, but how do you implement the precision and sound text groups that are given to us, for example?
Yeah, actually, the thing is little tricky. Means sound check is kind of like a single assembly query, but this the precision check is little text synthesis engine also. So we didn't bother even slice. We thought it will be too clumsy to.
So, like at a high level, are you going to the concrete domain and then executing
No, for now, yeah, for now we have the logical specification of the concrete. So use an of the self-assembly software and try to get to answer the sumness thing.
Maybe related to that, I was wondering, could you switch to slide 10?
Sure.
Oh, yeah. So when you talk about positive and negative examples, do you actually assume that the concretization function, so that your concrete domain is finite and the concretization function always gives you the finite result because that's where you check the conclusion?
Yeah.
Okay. So like you only work with dialog connections on finite domains.
Yeah. Yeah.
So okay, that won't work for like trace collecting semantics.
Yeah, I mean, I will not say directly in finite domain. I mean, we work with these interval domains and all. So, do you say these interval domains are finite domains?
I mean that all elements of your complete domain are fine.
Yeah, yeah. It's about the searching, right? We try to find. It's all about how to search for an abstract value A and post value C prime, such that it violates a given transformer. All you want to check. Okay, you give me a transformer. Is there exist any value which is not included by this guy? That's the sum check we do. In precision check, we check there exists a value which is included but shouldn't be included. I think we can have to talk more about the formulation, how we do that.
Okay. All right. There are no more questions. Let's thank the speaker.